Hey, we're sitting here at section 4.6 related rates. Going to be honest, this is going to be hard, okay? It's going to be hard to put your brain around this, so we need to take the time and just sit here and listen, not just listen to my voice and go to sleep, but actually listen, okay? So here we go. In related rates, we're going to be trying to find the instantaneous rate of change for some quantity with respect to time. Notice respect to time, okay? So, hey, an instantaneous rate of change might be a derivative with respect to time. Let that sink in for a little bit, okay? So what we want to do is, what I'm going to do is, I'm going to give you guys some translate. I want you to give English. I want us to translate it into proper calculus notation, okay? Complete with fingers in the air, okay? So the area of a circle is increasing at a rate of 4 square inches per minute, okay? So here we are. So you guys can probably write this part, the 4 square inches per minute. So I'm going to go ahead and write that down real quick. 4, okay, inches squared per minute. So now I want to have my my calculus part written in this form. So it's going to be some fraction. It says with respect to time. Remember when we had dy dx, right? That was the derivative of a y with respect to x. So if I want respect to time, I think I'm going to want dt. Now how can I do the area of a circle? Well, the area of a circle, well, I can just go area. But again, they want to say that it's increasing at a rate. So a rate, that's the derivative of my area with respect to time, is now increasing. How can I deal with the word increasing? Increasing means positive. All right, you don't have to put the positive, but I'm just there for emphasis. Why? Because in the next example we have this. It says the volume of a cone is decreasing at a rate of 2 cubic feet per second. Again, take what you know, 2 cubic feet per second. Okay, 2 feet cubed per second. And it says it's decreasing, so decreasing, you got to be thinking, what is decreasing? Decreasing. Oh, that's negative. Okay. And now it says the volume of the rate at a rate. Okay. Again, per second, dt. Volume, perhaps v. And it's an instantaneous rate, so it's dv dt. And there it is. Okay. I want you guys to take a few seconds. I want you to do 2, 3, and 4. I'm going to pause the video, make you guys do it. All right. Bam. There it is. Those are your answers. Check them over. Make sure they're correct. If you don't have any questions, make sure you come with them tomorrow. Here we go. Next. Okay. So next, we're going to do it backwards. We're going to say, okay, determine a possible meaning for the following expressions in sentence form. All right. So here I got dc dt is equal to 2 inches per day. Okay. So inches per day, C, I can think of some C words that are changing, so let's try circumference. Okay, so I can say the circumference. Now is it changing, and I have to ask, is it increasing or decreasing? It's positive, so I'm going to say increases at a rate of 2 inches per day. Yes, write it all out. I'm going to pause the video again. I need you guys to do 6 and 7 on your own. Here we go. And boom, here are possible answers. All right. So the surface area of an oil slick increases at a rate of 5 square yards per minute. And down here, the area of a triangle decreases at a rate of 4 feet squared per second. Excuse me. Again, notice decreases because of the negative. Okay, here we go. Next. So the reason why we do this is so we can start expressing and having different expressions and take the derivative with respect to time. So much like when we took the derivative with respect to x in our implicit differentiation, we had different y's, different, y squared, y cubed. Now we're going to take the derivative with respect to t. So the Church of Math rule, okay, the one that you just have to suck up and believe, is that it's going to be anytime you take the derivative of any variable, you have to add in there dy dt or dx dt depending on which variable it is. So when I have this equation here of y is equal to 5x squared minus a 6x plus a 2, what I'm going to have is, okay, take the derivative. Derivative of y is 1, which is dy, but I'm taking with respect to time, so this time dt, is equal to 10x, and in this case, since I'm taking with respect to time, I still need to have a dx dt minus 6 dx dt, because every time I have a variable, I'm always going to add that in there. Plus a, well, the derivative of 2 is 0. So now they say find dy dt when x is equal to 4 and dx dt is equal to 2. What I'm going to have here is dy dt is equal to 10 times 4 times 2 minus 6 times 2. So I have here 80 minus 12, which is equal to 68. So dy dt when dx dt is 2 and x equals 4 is 68. All right. So now we're going to actual problems. Okay. And there's a process that you need to follow every time. And I'm going to stress this enough. You take this, okay. This is one of those things you're going to write in there. This is important. This is gets starred. This gets the little hearts. This gets the big star like that. Okay. However you want to phrase it, this is important. So these are the 5 steps you're always going to follow. Draw a figure if possible. Assign variables and translate them into calculus. Relate the variables with a formula or an equation. Differentiate with respect to time. And then substitute in the given information and solve for a required rate. Never, ever substitute values for quantities that change until after you take the derivative. Very important. Okay? So what does this look like? Here we go. So, first thing, example, a pebble is dropped into a calm pond, causing ripples into the shape of concentric circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, find the rate at which the area of the disturbed water is changing. Wow. All right, so these are some intense problems that we need to translate into calculus. Okay. First thing is concentric circles. Okay, the radius r is increasing at a rate. Radius is increasing at a constant rate of 1 foot per second. So what are they telling me? They're telling me that my radius is changing at a constant rate of 1 foot per second. That's that translation. Okay. And now what they're saying is they want me to find what? Find the rate at which the area of the disturbed water is changing. Oh, they want me to find the rate of area. So they want me to find dA dt, the rate of the area changing per time, when r is equal to 4. So here's all my given information. Great. Now let's go ahead and draw a circle, or a diagram. So here I got my water ripple. It's growing. It's not always perfect. Here's where the point where I dropped my little rock. My radius. Okay, it's growing. They're talking about area of a circle and a radius. So you have to ask yourself, how can I relate area of a circle to a radius? Area, circle to a radius. How could I relate that? Oh, we got this formula, right? Area of a circle is equal to pi r squared. Oh, okay. Well, now let's go ahead. Now I have a formula that relates the two. And you have to ask yourself, what is changing in this formula? Is there anything that is absolutely positively staying the same? Is my area staying the same? No, because the circle keeps getting bigger. Okay, so I'm not doing anything to that. Is my radius staying the same? No, it's changing. So even though this is r is equal to 4 over here, do not put it in now. Okay, you have to wait. So wait for what? Well, I want to find dA dt. So how do I do that? I've got to take this and take the derivative with respect to time. So that's going to be derivative with respect to time. dA dt is equal to, now look here, I have a constant times a variable. Okay, so it's going to be 2 pi, constant stays, r, reduce my power by 1, times dr dt. Okay. Now that I have this relationship, now I can go ahead and plug things in. I know these things. I know that dr dt is 1. I know that my radius is 4 at a specific time. So I'm able to see that dA dt is equal to 2 pi times my radius, which is 4, my dr dt, which is 1. And I plug it all the way in. I multiply it out, and it's 8 pi. Yay! Not done. 8 pi what? 8 pi what? Area. It's in feet. Feet. The area means it's going to be feet squared. How fast? Per second. Wow. Okay, which is almost 24 feet squared per second, which is large. Actually more than that. Okay. Sucking in. All right, we'll be going to the next one. All right, so I'm going to skip example 2 for this section, and I'm actually going to go. All right, so example 3, highway chase. Ooh, this sounds exciting. So a police cruiser is approaching a right-angled intersection. All right, so as I'm reading this, I'm going to be doing some drawing. So let's do a right-angled intersection here. All right, so right-angled intersection. Right-angled intersection. There we go. All right. From the north. Okay, so from the north. So he's the guy coming up here. So he's a cop car. We'll make him blue. He's coming from the north. All right, we'll even give him some red lights. The more realistic you make your drawings, the better they'll be. Okay. So then all of a sudden, okay, so let's go and all right. Is chasing a speeding car that has turned the corner and is now moving straight east. So here's this guy. This guy's over here, moving straight east. Okay. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east. So now when we get to this point, guys, we have to be careful on what we label. If we start labeling this as 0.6 and this is 0.8, what our problem is going to be is that that's saying that that is static, that is not changing, and that's not the case. We're taking a picture. We're not, they're not standing still just for us. They're still moving. So I'm going to go ahead and I'm going to say, well, let's go ahead and relate these somehow. So if I'm going to relate these, okay, this is still moving. This is still moving. Okay, so let's call this P for police, and I don't know, we'll call this one C for car, or chase, yeah, C. Okay, so we have to be careful. So in other words, when they start saying this here, they're saying when P is equal to 0.6, okay, and the car, C, is equal to 0.8 miles to the east, the police determine with radar that the distance between them and the car, ooh, that's going to be changing too. So that has to get a variable. That's going to be D. And it's saying that determine with radar that the distance between them, okay, and the car is increasing at 20 miles per hour. So dt is equal to 20 miles per hour. If the cruiser is moving at 60 miles per hour, so that's dp dt, miles per hour, what is the speed of the car? Find dc dt when all the above is true. Wow. So how can I possibly relate the P, the D, and the C? They're forming, a triangle. But you know what? This 60 is bugging me. Why is it bugging me? How is P changing? Is P getting bigger or is it getting smaller? As the car is going down this way, is P getting bigger or smaller? P's getting smaller. So P is decreasing. So since P is decreasing, guess what dp dt? It's negative. We need to be careful with these, okay? Need to be careful, okay? They won't always say decreasing. It's how is it relating to our model that we're building, okay? So now I got this right triangle. Well, the only thing I really know about right triangles, I know that p squared plus c squared is equal to d squared, right? Good old Pythagorean theorem. I take the derivative of this with respect to time, and what I end up with is 2p dp dt plus 2c dc dt is equal to 2d dd dt. All right, so now I'm going to start plugging stuff in, right? Because I took the derivative with respect to time, I'm going to start plugging things in. So here we go, we're going to plug things in. I get 2 times p. At that instant, this thing is happening. I'm taking my picture now. 2 times 0.6 dp dt is a negative 60 plus 2. C is a 0.8. dc dt is what I want to find, so that's okay not to know it. Is equal to 2 times d. Oh no. I don't know what d is. dd dt. Oh, that's 20. Okay. How can I possibly find out what d is? I need to know that. But again, I'm at the instant. So when I'm at the instant, it is okay for me to plug in stuff. It is not okay for me to plug in stuff when I'm not at my instant. So because I'm at my instant right now, I can say that 0.6 squared plus 0.8 squared is equal to d squared. I can find out at the instant that all these measurements are happening, what is the distance between the two? And when solving, I find out that 1 is equal to d. Oh, 1. Okay, so I'm going to plug that in there. Dink. At that instant, it's exactly 1 mile apart. And now I can go ahead and now multiply things through. What I'm going to find out is that this is a negative 72 plus a 1.6 dc dt is equal to a 40. Subtract the 72 from, or add 72 to both sides. I get 1.6 dc dt is equal to 112. And then I divide by 1.6 on each side, and I get that dc dt is equal to 70 what? Miles per hour. Now you guys might be thinking, oh, geez, what did I just find? You found some amazing stuff. You found out this car, given information, okay, you're able to find out how fast a car is traveling without actually physically seeing what the speed is on the speed limit. How cool is that, right? Okay, so what I'm going to do is I'm going to stop here. This is a lot to take in. All right, I want you to try some of them. All right, try some of the problems. Okay, look at the homework, try some of them, and then tomorrow you get to watch some more examples. Come with questions.